In this video, we'll be continuing with the strengthening mechanisms in solids. Uh, we discussed grain size reduction and solid solution strengthening in the previous video, and in this part, we'll be discussing strain hardening. Okay, so basically, what is strain hardening? Strain hardening is when a metal is strained beyond the yield point, and increasing stress is required in order to produce the additional plastic deformation, and then the metal apparently becomes stronger and it is more difficult to deform it. So basically, this is the strain hardening, and strain hardening is also known as work hardening. You can see over here that the phenomena where ductile metals become stronger and harder when they are deformed plastically is called strain hardening or work hardening. So increasing the temperature, when we'll be increasing the temperature, the rate of strain hardening is being reduced, and again the uh, strain hardening and low temperature is also known as cold working. Basically, when we'll be deforming our material, when we'll be applying the load, our material will be deformed at room temperature. So that deformation with the applied load is called the cold working. Okay. So while cold working, there is strain hardening. So during plastic deformation, dislocation density increases, and thus their interaction with each other, resulting in the increase in the yield stress, as we discussed in the previous video in the strengthening mechanism. So you can see that there is a stress strain graph, and this part would be the yielding stress, and this is the elastic modulus over here. So this there will be two strains produced when we'll be stretching, or when we'll be applying the load. Our material will be stressed or compressed. So when it will be when we'll be studying a stress strain curve. So after the elastic limit, the material will be deformed plastically. Let's assume up to 0.3. So when we'll be removing the load, so it could come back to its original position, but there will be some strain now will be remained because there is plastic deformation as well as the elastic deformation. So the elastic strain would be recovered. However, the plastic strain would be still uh, remain in that. That is basically work hardening. During strain hardening, in addition to mechanical properties, physical properties also change. We now know that the mechanical properties are changing. That the strength is increasing and the ductility is being compromised. But there are also some physical changes. That is, a small decrease in density is being observed in some cases, an appreciable decrease in electrical conductivity, and a small increase in the thermal coefficient of expansion is being observed in some cases. Okay, and the reactivity is also increased, as we discussed in the previous video, that the dislocation would cause hindrance at the grain boundaries. The dislocation movement would be resisted, and hence there would be a high energy grain boundaries, which would decrease the corrosion resistance. That means your material would be easily corroded. Okay, so the deleterious effects of cold working can be removed by heating the material to a suitable temperature. That is called annealing. Annealing, we'll be studying annealing in detail when we'll be doing the heat treatment, and we'll be studying the heat treatment processes. So I'll just give a flavor in this video of annealing. So when we'll be doing the cold working, our material will be highly stressed, and so the strength would be increased. So in order to remove the residual stresses, we'll be doing annealing. What we'll be doing is we'll be heating our material, and then we'll be holding it to a certain temperature, and then we'll be cooling it down. So that restores the original properties in a material before the cold work was being done. It consists of three stages, that is recovery, recrystallization, and grain growth. In industry, alternate cycles of strain hardening and annealing are used to deform most metals to a very great extent. So what has been done in the industry is, for example, if we have a sheet and we have to bend it 4 times. So what we'll do is we'll bend it one time, and then we'll be annealing it again. We'll be bending it another time, and then we'll be annealing, and we'll be doing it on cycles so that the original properties are being restored and the material is not broken due to very high strength, because the ductility is being compromised when the strength is increasing while cold working. Okay, so here is a stress strain curve. You can see that there is a yield stress, yield strength, and up to this point, the ultimate tensile strength point, there would be strain hardening, and after that there would be necking. So we are not interested in this area, but rather we are interested in this area. So this is how the strength is increasing due to work hardening or strain hardening in this area. And after a certain limit, after a certain threshold, the strength would be decreasing since there would be necking involved now. So the impact of cold working, we discussed what is cold working is. Cold working is deforming a material, deforming a metal especially at room temperature as to increase the strength. So cold work is increased while we can see that there is a stress strain curve, and this is of the same material. This is of a low carbon steel, and in which this is at a 0% cold work, that is the green figure, which does not have been cold worked, and the blue line is 4% cold work, and the red line is the red curve is being 24% cold work. So we can observe over here that this is the strength, the tensile strength. This is the UTS for 0% cold working. This is the UTS for 4% cold working, and this is the UTS of 24% cold working. So you can see that the tensile strength is increasing. In addition, the yield stress, the yield strength is also increasing. You can see over here. This is the yield strength now. And however, the ductility is decreasing. You can see that the total area toughness is also being compromised, and the ductility is also decreasing. This is another analysis of cold working. You can see that the percentage of cold working of copper alloy, you can see that while the percentage of cold working is increasing, the strength is continuously increasing, the yield strength. Similarly, the tensile strength is also increasing. However, the ductility is decreasing. So we'll be taking ductility in terms of percentage elongation or the percentage of reduction in area. So the effects of heating after the percentage cold working. 3 stages of we have to discuss over here. Okay, so you can see that this is the tensile strength, this is the percentage of ductility, and this is the annealing temperature. Okay, so while the temperature is increasing, you can see over here that this is the temperature in percentage, sorry, in degree centigrade. You can write it over here or you can write it down there. It's up to you. So when you can see that this is 100 at 200 and 300. So while the temperature is increasing, now you can see that the tensile strength is being decreasing. Okay, because the materials because the material is rearranging itself, it is recrystallizing itself, and grains and the atoms are arranging as they were before the cold working. Okay, so and the ductility is also being restored as it was before cold working. So you can see there are 3 stages. There is recovery, recrystallization, and grain growth. So in the first stage, the stress is being recovered, the residual stress, and then the atoms in the second stage, and the orange one, the atoms are recrystallizing itself, the grains are recrystallizing, and further the grain is being the grain size is being increasing. There's grain growth, the small grains which are nucleated are now growing. So the ductility is, you can see over here, is increasing. So this is the graph of 1 hour heat treatment to at annealing temperature. That decreases the tensile strength TS and increases the percentage elongation, which is the ductility. So the effects in this for the cold working are reversed. Okay. So during recovery, some of the stored internal strain is relieved by virtue of the dislocation movement. Again, the atoms since are rearranging itself, and in this we are not applying any stress. Okay, we're not applying any load, so there is no stress generated. The stress is being relieved. Uh, as a result of enhanced atomic diffusion at elevated temperature, there is some reduction in the number of dislocations, and dislocation configurations are produced having low strain energy. So while the atoms are diffusing and it's in itself, so while the atoms are diffusing at a higher temperature, sorry, there is some reduction in the dislocation. The number of dislocations are being reduced, and some new configurations of dislocation are also being produced, which are of low strain energies. Okay. So in addition to that, physical properties such as electrical properties and thermal conductivities are also recovered, which were being compromised while cold working. Okay. So, and this is now recrystallization. New grains are being formed. You can see in these two figures that it has a low dislocation density, and the atoms are small, and the consumed the grains which were formed in cold working were now consumed. So you can see over here that this is a 33% cold worked brass, uh, and you can see that these are the grains. These are the stretched grains due to cold working, as we discussed in the last video as well. And now when the recrystallization is being done, there are new grains being formed over here. The old ones are being diffused and the new ones are being formed. This is new crystal is nucleated after 3 seconds at 580 degrees centigrade. So this is a sample of brass. So at 580 degrees centigrade, for on holding it for 3 seconds, the recrystallization is being now observed. You can see that after 4 seconds now, and after 8 seconds, there are new grains are being formed. So these all grains are being diffused, and the new grains are being formed. So recrystallization temperature TR, basically the recrystallization temperature is the point of highest rate of property change. Okay, so after that um, we'll be going towards the melting temperature. So we are not melting our part or our material in this case. However, every stage that is of recovery, recrystallization, and grain growth is being done in the solid form. Okay, so the recrystallization temperature is about 0.3 to 0.6 Tm, that is 30 to 60% uh, of the melting temperature in Kelvin. So due to a higher diffusion annealing temperature, the Tr is higher. Shorter annealing time would be higher Tr. If you want to anneal in a very shorter time, so the Tr, the crystallization temperature will be taking a higher crystallization temperature for a very short time. And if we are doing for longer time, so the TR would be somewhat low. So the higher the percentage of cold work, the lower the TR and the strain energy. Okay, so if the percentage of cold working is very high, so we'll be selecting a low recrystallization temperature. However, we'll be holding it to that temperature for a certain time, so that all the atoms are recrystallized, or the grains are crystallized, and this effects of strain hardening are reduced. So for pure metal, a lower TR due to dislocation movement, easier to move in pure metals and lower TR. So in pure metals, the dislocation movements is very easy because there are no foreign atoms, or there are no impure atoms, there are no impurities, there is no solid solution, so the movement is very easy. So it can be done on a very lower TR as well. Okay. So now grain growth. So after the recrystallization is done, um, at a longer time, the large grains are consumed, and the smaller ones. You can see that after 8 seconds, as we discussed in this, after 8 seconds, the new grains were produced. And now, if we hold it to 15 minutes, so these grains are, you can see these grains, the grain size of the grains increase their size. The fine grains are not now uh, grown into coarser ones. You can see that. So sometimes it is desirable and sometimes it is not. It depends on your application. If we want coarser grains, if we want optimum properties, we selecting the coarser grains. If we still want a higher strength, we'll be going with this fine grains. So here is the again that graph which we discussed in the previous slides. We see that this is the TR, this is uh, the recrystallization temperature line, that is about 780 degrees degree Fahrenheit. Okay, and this is the recovery region, this is the recrystallization region, and this is the grain growth region. Okay, so the tensile strength is now being decreased, and the ductility is being restored to the original one. Okay, so here you can see that these are the cold work grains which are elongated because we will be applying the load, and these grains are stretched. After that, when we be taking it up to a higher temperature in the recrystallizing region, the grains would now be starting to consume due to atomic diffusion, and after some time and with increasing temperature, the new grains will be formed. Okay, and when all the new grains are being formed, so now in the grain growth region, we can see that these grains are being uh, growing into the coarser ones. Okay, and to that you can see that the tensile strength is reduced and the ductility is increased. So if we want to select a certain property, a certain uh, we can see that certain limits for certain values for tensile strength and ductility. So we'll be this is the graph, which is again of the copper law. So we'll be selecting that temperature, which gives us the optimum tensile strength and ductility. So if we select, for example, this temperature of 600, it would give us the tensile strength of 500 megapascals, and the ductility of around 30%. Okay, and if we further want to increase the ductility, let's say about 40%, so we'll be selecting our TR, that is the tensile, sorry, that is the recrystallization temperature at about 550, I guess, at about 500 degrees centigrade, 550 degrees centigrade, and on that point our ductility would be, sorry, our tensile strength would be around 40 megapascals. Okay, so whatever value of tensile strength and ductility we need, we'll take that account, and then we'll be selecting our annealing temperature. Okay, so that was all in the strengthening mechanisms of solids. Thank you.